basically, here we introduce marked states which represent goal states. Okay, represent the objective of our control. So states that we want to reach. And here we define a marked language as a subset of the closed language, which has the peculiarity to contain only the strings, those strings which bring you to a marked state. So they are basically the path towards your objective. So the marked language contains the behavior, the so-called legal behavior. So the set of those strings which brings you to a marked state. And here we define the different things the treating operation, which is the operation that gives us back the accessible and co-accessible part of an automaton. And then we define the subautomaton relationship. Then we define synchronous composition. And we define the refinement as well. Okay, just as a pure extension, and of course equality. Okay, so today we do the same with a further extension, which is this one. So now we introduce a sixth element in the definition of automata. These automata are called an automata with marked and forbidden states. So XA is nothing more than a subset of QA, as it is for NA. Okay? NA is nothing more than a subset of the set of states, which is our mathematical way to label states. Instead of introducing a label for states in order to say that a state is marked or a state is forbidden, we simply say that a state may belong to the forbidden state set or the marked state set. Okay, so that's our way to label states in order to avoid confusion with the real labels that are the best. Okay. So forbidden. Forbidden states. So it may seem not necessary to introduce forbidden states, okay? Because actually we are modeling things, we are modeling the behavior of production systems, okay? Why should we model something that then we declare as forbidden? So it seems strange that we model something and then we say this something is forbidden. It's better not to model it. As you can easily understand, actually, it may be easier sometimes, not always, but sometimes to say that something is forbidden than to say that all the rest is permitted. Okay? So sometimes it's easier, simpler to make a model. Maybe the model, I take a small amount of time to build up a model, and in doing like this, maybe I create some more states than necessary, and then I declare something, one state is forbidden. It's easier. Or maybe it's easier because for a robot, for example, I can define a lot of activities or missions he can perform. For example, he can clean the windows, open a window, close a window, open a door, close a door. And then I would like to say that this robot can perform all these tasks, all these missions, in any order. So with a lot of infinite many repetitions of them. Okay? And then I would also like to say that this can be executed in any order. So the robot can open the door, then close the window, and then close the door, and then clean the window, and so on. Okay? That's a normal thing to do. But maybe there is just one combination that is not meaningful. Maybe there is, you cannot open the window and then clean the window. Maybe, I don't know. So it's easier to say that the robot can do many things, so 10 missions in any possible combination except one. So I would mark this combination as forbidden. Okay? It's easier to say that one thing is forbidden instead of saying that all the rest of possibilities are allowed. Okay? And also, if we model the behavioral system in a modular way, again, I can model one robot with a lot of activities. I can model a second robot with a lot of activities, which are straightforward without any restrictions. But when they work together, maybe there is some problem. So if there are robots welding a piece of metal together, maybe they can collide if they work exactly in the same space. So the thing that I should prevent is collision, of course, and so I may say that when the robot one is painting, the other robot cannot welding or something like this. So again, in the composition of modules, some forbidden state may arise. So actually, this is something which is quite straightforward for us. Okay, it's not strange to model something that we immediately declare as forbidden. That's absolutely straightforward. So for these automata, again, we can define for sure the language of the automaton, the marked language of the automaton, but we want to define something related to forbidden states. Okay, and this is called the forbidden language. Okay. Written LX of A. So what is the forbidden language? The forbidden language is the collection of those strings whose prefixes end up into a forbidden state. Okay? So basically it means that it contains some strings that pass through a forbidden state. So the definition of forbidden string is a set of strings belonging to the closed language, such that the delta function of the automaton, starting from the initial state, applying some of the prefixes, not necessarily all the prefixes, intersection with the forbidden state is non-null. Okay. What's the meaning of it? The meaning is exactly what I said before. I'm using again the delta function with a slight extension of its meaning. You remember that originally the delta function was from a domain made by the Cartesian product of QA and sigma A and a codomain into QA. Okay. So that's the original definition. There we are extending it because of two reasons. This is not an event, okay? This is not an element of sigma A, capital sigma A, but this is a set of strings. It's not even a string, but it's a set of strings. And in particular, this is the set of all the prefixes, the string S. Okay? So all set of all the leading substrings of S. So on the left hand side of the string, okay, all the prefixes. But we already did this extension, and it's absolutely obvious. If you write here a string, it means you start from this state, and then you apply one by one the event of the string. Okay. If you have a set of strings, it means that you repeat this procedure for all the strings in this set. Okay. So basically, if here you have 10 strings, you have to start from the initial state, applying 10 strings one by one. And in the end, you will obtain 10 different, in general, 10 different states. Okay? You collect these states into a set. Okay? So if you apply the delta function with a set of strings, you will obtain a set of states instead of a single state. Okay? That's quite natural. So this is why I put here intersection symbol. So the intersection, as we know, can be applied only to sets. So this is a set of states which I can reach starting from the initial state, applying a set of strings, okay, and the set of forbidden states. Okay. So basically, this is nothing more than the formalization of what I said before. So S, small s, belongs to this language if it brings you to a marked state, or some of its prefixes brings to a marked, forbidden state. Okay? Some of these prefixes brings you to a forbidden state. Okay? So it means that you pass through a forbidden state. Okay? If you pass through a forbidden state with the string S, this string belongs to a forbidden language. Okay? So it's a forbidden string. So it's a bad word. Okay? So a bad string, or a forbidden string, is a string which passes through a forbidden state. So it's not like the marked language where you want to arrive into a marked state. In this case, you are forbidding something, so there is a dangerous point. You cannot go across a dangerous point. So all the strings after the dangerous point must be forbidden. Okay? So that's the general idea. So, do you think that this language is prefix closed, for example? Just as a general idea. How many of you think that this is, in general, prefix closed language? How many of you say that this, in general, is not prefix closed? Okay, so it's not prefix closed in general. Okay, it's not prefix closed because basically, if you start from the initial state, if you apply a string and you reach a forbidden state, and no other forbidden state in between, all these prefixes does not belong necessarily to the forbidden language. Okay? So the fact that if you go exactly in this corner and you find the problem, this does not mean that you find the problem at every step from here to there. Okay? So in general, this is not prefix closed. Okay? make an extension to a previous example. Now, let me first include the definition of the languages and then we'll give you an example. So for this automaton, I can define LA, LN, okay. I do not change this definition. So if I ask you to compute the math language of a forbidden automaton, you perform exactly the same operation that you did before. But for sure, I need to do something if I introduce forbidden states. Okay? So basically, if I want to reach my goal, and during the way to my goal, I encounter a forbidden state, for sure I have problems. Okay? It means that I cannot reach this goal. So I want to be able to combine these two. So for this reason, I will introduce two other languages. Okay? These are called primed languages. Okay? Simply because of the usual lack of imagination of those who invented the theory. So they didn't know how to name these languages, so they put a prime sign, and so they define them. So in Italian languages, linguaggi primi, che mettono un apice con tutto. So we define the prime language of A, which is nothing more than the language of A minus LX of A. And similarly, the marked prime language of A, which is the marked language of A minus LX of A. Okay. So these are the prime languages, which are the good, finally good languages, because basically I removed all the bad words. I removed from the language all the bad words. So all the strings that come across a forbidden state. Okay. Would you expect that L prime of A is a prefix closed language or not? Just as a guess as before, how many of you think that L prime of A is a prefix closed language? How many of you think that L prime of A is not a prefix closed language? Okay, so the result is that this is a prefix closed language by construction, because you start from a prefix clause and you remove some, let me say, longer strings, the longest strings which pass through marked states. So what remains is closed by the two. For sure, the last one. Okay, let's make an example. Usually, just to simplify, we mark forbidden states in different ways. Sometimes we put a square. I usually use an X sign, so a cross, okay, just to mark a state clearly as forbidden. Okay, so marked states are usually circled very thickly, and forbidden states are marked like this, so it's easier to understand. Even if in literature there are different signs. So let's make an example like this. We start from, it's the same example that we've seen last time. Okay. there are two different arcs. The first one is labeled with C, and the second arc is labeled with D. Okay, but like this, C and D. Okay, this is too complex to draw, and so we prefer to write this. This is just a shortcut. This is not an extension. Okay, it's just an abbreviation. Okay. There were a few other states around that we can remove. We already understand that there are some other, there could be some other states which bring you somewhere, but all these states are not reachable, so they will never contribute to any language, so we can remove them. So, last time we marked this state, Q3, and now I forbid Q2. Okay? So, last time we computed it, but it's very easy, so we can compute it again. The marked language and the language of the automaton, just to recall everything. So the language of the automaton is epsilon. It means that I can stay to 0. A and B as single event strings. Then I have two event strings, like this is B. So BD, BC, ACAD, and that's it. For marked language, we have BC, so this part will mark the state, and then this two. So AC, AD. So clearly we make the different set, we compute the different set between the forbidden language, the forgotten. What is the forbidden language of this automaton? So for sure B, that brings you directly to a forbidden state. So this string here. But also BD. Okay. BD is a string S belonging to the language of the automaton, such that one of its prefixes, for example, the prefix made only of the event B, brings you to a forbidden state. Okay? So that's the definition. So, BD and BC. So let's compute the difference now. So we have, so this is a prime of A, so epsilon. A, C, B, and okay. So we observed that what we said before, in this example, it happens right away that the forbidden language is not prefix closed. Okay. While the prime language of the automaton is prefix closed. This is what we expected, and we find in this example. finally, we compute the marked prime language, which is the difference between the marked and this one. So, ACE. Okay. So I should remove from LM, for the marked language, the elements of LX, if I can find them. Okay, and this is not practice closed as expected also. So basically, what we are doing is trying to refine a little bit the definition of the automaton. So now we are building a rich, more or less a rich format, because in the end we are able to specify something that is good for us, we call them marked states, and something which is definitely bad for us, and we call them forbidden states. And then we compute the difference, which is the primed marked language. So definitely this is our goal. Okay, we want to modify the behavior of the automaton so that this is the executable part of the automaton. Okay. So as we defined the arch, co-arch, so the accessibility function, co-accessibility, the trimming, and so on, we can do something similar also here. Okay. So for example, we can remove forbidden states. Okay. Those states cannot be reached in any way. We cannot come across these states, so I can safely remove those states. This operation is called purging. Okay, so if I remove forbidden states, I obtain a subautomaton by definition, which is a purged automaton with respect to the original automaton. So basically, we use usual notation. We take the first letter of this term to define the operation. So PU of A is the function that gives us back an automaton, which is the purged automaton. So the automaton A after the removal of the forbidden states. So what happens if I compute the language of the purged occasion? So I take the automaton A, I remove the forbidden states, and then I compute its language. Okay. So we don't prove it because it's simple, but this is exactly the primed language of A. Okay. And this expression is very, very simple to understand, but what's the meaning? What's the intrinsic meaning of this expression? That basically it means that I can operate with events or strings or languages or on states, and I obtain exactly the same result. So this theory is built around this concept, which is very nice for us. Okay? So I can take an automaton, declare something forbidden, then I can compute the forbidden languages, and I can compute the prime languages. Or I can remove directly the states. Okay, instead of removing events in strings, with this operation here, I can physically remove the states, and I obtain the same thing. So this is a powerful result, even if it's straightforward. So it's not difficult to understand. But basically, this is why we keep on switching between states and languages. So when it's easier for us, we will talk about states. When it will be easier to talk about language, we will talk about languages, because it's the same. We can perform operations on automata, removing or working on languages, or working on states, and the result does not change. Okay? So similarly, I can compute the marked language of the purging of A. It means I take the automaton A, first I remove the forbidden states, then I compute the marked language. And this will be exactly this one. So this will be the marked prime language of A. Okay? So removing states or removing strings brings me to the same result. And what about the forbidden language of the purging of A? So I removed all the forbidden states, so I have no more forbidden states, and so this is the empty set. Okay? Let's do that. When I write all these things, as we did for example, simple composition or training or whatever, I'm always intending this function actually as the result of the operation, purging, training, simple composition, or whatever, and then applying the accessibility function. Okay? If you remember, I gave, for example, the synchronous composition, I gave the formal definition of synchronous composition, okay, through which I should compute the Cartesian product of the states of the two automata that I want to compose, okay. And then I gave you the quick definition, so you just follow events as they occur in the operand. Okay, you just follow the events, because those events which are not executed in A and B will not be executed in A and B. So it's useless to ask a question, ask ourselves the question: can I execute the event if the event is not executed in none of my automata? So we follow basically the arcs. In doing like this, actually, we do not compute, strictly speaking, the synchronous composition, but only the accessible part. But actually, the accessible part is actually what we need, what we want to look at. So actually, I write 2, but actually, I mean the accessible part of the 2 of A. Okay, this is always present, this function, because states which are not reachable will never contribute to anything, so they should be removed, like H4, for example. Okay? They never contribute to any language, so we remove them, and that's it. We can also recall one simple let's just go on. That's it. So, I think it's clear to everybody. Are there any comments or questions from your side? Okay, so let's extend the classic definition that we have already studied, social automaton, composition, and so on. In order to do this, I need to play the same game as we did last time. So last time we said if I have a fifth tuple, so an automaton upon which I express my desires, okay, an automaton out of which I underline some states as goal states, I can compute, it's trivial, I can compute the original four tuple automaton that we called automaton non-marked automaton, okay, simply removing this set, okay. So if I give you a five tuple, you just remove the last element, and what you are left with is a four tuple, which is exactly the same. So we can call this as a non-marked counterpart of a marked automaton. Okay, so we play the same game, and if we are here, so if I give you a sixth tuple automaton, which means an automaton on which I express my desires in terms of marked states and forbidden states, I can go back to a fifth tuple, okay, just removing this information. I remove the information on forbidden states, and what remains is a non-forbidden automaton, okay? And this will be obtained by this as a non-forbidden, non-marked counterpart of this, okay? That's very easy. So doing this way, it's easy. You just neglect something. Doing the other way is always not more complicated. So I can transform a non-forbidden marked automaton into a forbidden automaton, saying something here. I have to establish a notation, okay, a conventional notation to define what happens to marked states. So if I give you a fifth tuple, it means that I express my desires in terms of marked states, but I have nothing to say about forbidden states. Okay, otherwise I would have this formulation. So if I give you this, it means I have no desire to forbid anything. Okay, so the forbidden version of a marked automaton will be a forbidden automaton where xa is equal to the null set. Okay, so this can be regarded as an automaton QA, sigma A, IA, delta A, and A empty set. Okay, so if I give you just 5 elements, it means I have no desire to forbid anything. So I can formulate it as a forbidden automaton with no forbidden states. That's it. Okay, you remember also what we did here. Okay, we formulated QA, sigma A, IA, delta A, and A. Sorry, QA. Okay, so a normal automaton can be regarded as a marked automaton. This is what we did last time. With all states marked. Okay, it means here I do not need to mark anything as a special target for my automaton. It basically means all the states are good, are equally good, so are equally marked. And so this is our common way to say that all the states are equally good. Okay, all the states are marked. Okay, so this is only a mathematical notation to switch between automata. Okay, so in this case I can always combine everything and find out everything. Now let's go directly to the definitions. So we start as usual with the subautomaton relationship. We will say that an automaton A as a sixth tuple, so as a forbidden automaton, is a subautomaton of another forbidden automaton, and we will use the usual notation. There is no need to introduce something new. Subautomaton of QB, sigma B, IB, delta B, and B, X, B, that's it. Okay, so we say that A is subautomaton of B in the forbidden automaton world if the two non-forbidden counterparts stay in the same relationship. So the non-forbidden counterpart of this automaton is a subautomaton of the non-forbidden part of this one. Okay? Plus a condition on the last, on the novelty in this case, which is related to the forbidden space. Okay? You remember we played the same game here. Okay? We said that for marked automata, a marked automaton A is a subset of the marked automaton B if the two counterparts, unmarked counterparts, stay in the same relationship. So the unmarked counterpart of A is a subautomaton of the unmarked counterpart of B, plus a condition on the marked states. And we said marked states of A, subset of NB. You remember? Now, the condition that I add here is only is this one. So I don't write all the stories or the non-forbidden counterpart of A. Let me write it. Non-forbidden counterpart of A, subautomaton of non-forbidden counterpart of B. This is not a formal notation. This is because I'm lazy. I don't want to write everything as usual. And a condition on this. In this case, it's the reverse. So see, XB contained in XA. So it's the reverse as this one, as it was in the case of marked states. Okay. So if we consider just marked automata, a subautomaton should mark a little less than the superautomaton. This is our notation. Okay. On the contrary, for forbidden automata, we do the reverse. The subautomaton should forbid more than the superautomaton. Okay? That's the opposite. So basically, this follows the way of thinking that a subautomaton should be smaller in some sense with respect to the superautomaton. So what's the meaning of being smaller? Being smaller means forbid more. Okay? This is the idea. Okay? So we have to swap A and B with respect to MA and B in the previous definition of subautomaton. Okay? So the subautomaton A should forbid more than the superautomaton. Sorry, the subautomaton A should forbid more than the superautomaton B. That's the meaning. Okay? You have more forbidden states in the smaller automaton. Okay? It's very complicated to say the relationship between the forbidden language of A and the forbidden language of B when A is subautomaton of B. That's extremely complicated in general because being a subautomaton basically means that you remove some states or some arcs or both, okay? And in doing like this, you may transform some states, some forbidden states, there is non-reachable, okay? So it's very complicated to write a formal expression. But I expect, in general, I cannot prove because it's wrong also, but I expect that in general, the forbidden language of A is a bit bigger than the forbidden language of B. But what I can contrary prove is that for the prime language is all. So if I is equal to automaton of B, then the prime language of A is contained in the prime language of B, and prime marked language A is contained in the prime marked language of B. So this is actually the rationale behind this hypothesis here. To read a little bit more means that the prime languages stay in a relationship, one containing the other, which is what we expect. Okay. Okay. Given this, basically we have nothing more to say. We can define equality without any effort, as we did for math automata. So we say that A is equal to B, if and only if A is subautomaton of B and B is a subautomaton of A. Okay, that's the strong equality or equivalence or isomorphism. Okay, there is also the language equivalence that we usually do not use. It is strong or deep, strong or deep equality. Okay, the language equality is not so important. It means sigma A equal to sigma B, LA equal to LB. Marked language of A equal to marked language of B, forbidden language of A equal to forbidden language of B. So all the languages are equal. Okay, but we usually do not use language equivalence. The last effort, let me say, is the synchronous composition. Okay, so synchronous composition between forbidden automata. Okay, that's the last extension that we make. So A synchronous B, where A and B are of this type. Okay, forbidden languages. Forbidden automata. Okay. So we are extending the same operation as we did for marked languages, marked automata. Okay, and you remember that the extension was really smooth in the sense that again the result is not a number, it is an automaton. So the composition of two automata is again an automaton, as it was here in these cases. Okay, and in particular, if I'm composing two six tuple, I will obtain a six tuple automaton. Okay, so the definition is obvious. So the result is just a six tuple. So 1, 2, 3, 4, 5, 6. That's the result. Okay? And I think it comes with no surprise that the first 5 elements here are very easy to compute, because the first 5 elements will come from the previous definition. So the synchronous composition between the non-forbidden counterpart of A with the non-forbidden counterpart of B. Okay? So I'm exploiting the previous definition. So what I should say is this one. I say, and I don't even write because it's really trivial. So the non-forbidden counterpart of the synchronous composition is obtained by the synchronous composition between the non-forbidden counterpart of A with the non-forbidden counterpart of B. Okay? It takes 15 minutes for me to write everything, but I think you understand. So the only novelty, again, is what to do with the last element. Okay? And it's slightly more complicated, but not much. So the forbidden state here, A synchronous B, let's call it a case, A synchronous B. This forbidden state here is composed as QA Cartesian XB union XA Cartesian QB. Okay? You may put brackets if you want, not necessarily. And again, the formula is long, but actually the meaning is straightforward. It means that the forbidden states in the synchronous composition are made of couples of states in which one of the two states is, at least one is forbidden. Okay? So, if there is a forbidden state in A or B, whatever you obtain is forbidden for the synchronous composition. Okay? So, this again follows our idea that the synchronous composition means to find the synchronous behavior, so the common behavior between two automata. So the common strings, common paths between two automata. And the meaning of forbidden means I really cannot come across this state which is forbidden. So bring me everywhere, but don't ask me to go to or through a forbidden state. So if we go together and I have a forbidden state, I can go together with you, provided that you don't bring me to come across one of my forbidden states. And the same for you. Okay? So if we need to go to a restaurant together, okay, if you have some problem of intolerance and you cannot eat, I don't know, some kind of flour, we cannot go together in this restaurant. Okay, that's the meaning of the synchronous composition. Okay, if there is at least one forbidden state for one of the two automata, that's forbidden for the couple for the composition. Okay, that's the meaning. Based on this, we define the refinement, but actually I do not define anything because the refinement A refines B if and only if A synchronous B is equal to A. So basically this is exactly the same definition that we always gave, provided that now the meaning is with A and B 6 tuple. That's it. So the definition is basically the same. I do not need to redefine anything. Okay? Everything clear? So this basically defines what we made so far, the basic formulas that we are going to use. We are spending some time in the formulas because actually most of the things are hidden inside the definition, so we are spending a good amount of time because we need to understand them better. After this, all the other things are easier to understand. So we will do also a lot of exercises, more exercises than now. As an appendix to the modeling part, so the definition of the modeling framework, that for us is called labeled automata, so we are just doing labeled automata so far. As an appendix to this topic, we introduce labeled Petri nets. Okay. Why are we introducing labeled Petri nets? Because they are close to labeled automata, so the theory has been developed also for Petri nets. But especially because Petri nets has much stronger modeling power than automata. Okay, so I can model more complex behaviors with a small graph in Petri nets than with automata. Okay, so if I have many states in my system, in the case of labeled automata, I have to list them all. In the case of Petri nets, I can draw a small graph. Okay. So those of you who have done one of my exams in the first level, the bachelor level, have seen not the labeled Petri nets, but just the Petri nets. Okay. Now we introduce labeled Petri nets, which is an extension to Petri nets. Okay. But in this course, there are people coming from many different regions around the world. So I will briefly summarize Petri nets, okay, in order to let everybody reach the same level. So summarize means 1 hour, something like this, just recalling the basics. Okay. So first I recall the basics of Petri nets, and then next time I will introduce the labeled Petri nets. We will spend just a small amount of time in Zotra, okay? Because the extension is very, very simple to understand. So some of you who remember very well Petri nets, we will either take these few words as boring or as a review of something, or as a check to understand if you remember things correctly. So just normal Petri nets. Okay. By the way, we introduced labeled Petri nets because, as I said before, they are a powerful tool for modeling. They are not useful for synthesis of the controller. Okay, so we will use Petri nets just for modeling systems. Okay. So Petri nets is an extension of automata, normal automata, in the sense that they are made of a graph plus something else. And the graph itself is an extension of automata. So basically, the automata, or better, finite state machines, the finite state machines are automata without labels, more or less. So finite state machines are basically made of states and arcs, nothing more. So this is mathematically called a graph with one kind of node, which are called states. And then we have a transition between states, which we call transition function. Okay? This is graphically represented, the finite state machine is represented like this. State, arc, and another state. Okay? In the end, this can represent something, but not everything, so we need to add something. Usually we add a label, and we obtain labeled automata, which are different from automata because of the label. Okay? We are not here at the moment, we are just talking about standard Petri net, not labeled Petri net. So Petri net is starting from an extension of this notation. So instead of having just states and arcs, as you're doing now, we have two different kinds of nodes. Okay, so Petri nets have two nodes. Have places, nodes, places and transitions. Okay. The graphical notation is that for places we use again a circle. Okay. And for transition we usually use a bar. So usually places are like this and transitions are like this. This is just a graphical notation. But the graph itself is a little bit more complicated. Okay. Then there is the transition function. Okay. The transition function basically says who is connected with who. In the case of automata, you can connect one state with another state. That's it. In the case of Petri nets, you have two different nodes, and so you have slightly more combination. Actually, there is one strict rule which says that places can be connected with transitions, transitions can be connected to places, but you can never have that a place is connected with another place, nor a transition is connected to another transition. Okay, if you have a transition, not in this sense, but in the sense of transition function, you have to transit from a place to a transition, or from a transition to a place. You cannot transit from a place to a place, nor from a transition to another transition. Okay? There is a slightly possible misunderstanding about the word transition. Okay? So transition is here a node of the Petri net. Okay? But it's also a word in English. So transition means to change from something to something else. Okay? Okay, so traditionally we introduce Petri nets in an algebraic form, and we introduce the graph like this. So a set of places, a set of transition, and the mapping function, the flow function. The letter flow means, the letter F means flow, which is exactly the same meaning as delta function. It's just a transition function. And algebraically, we use this notation, so it's a subset of P Cartesian P union P Cartesian P. So it means that it's a set of couples. The first belongs to the starting node and the second belongs to the ending node. Okay? And if the first node is a place, then the second node is a transition. Or if the first node is a transition, then the second one is a place. Each couple represents one arc as usual. Okay? So for Petri net, I can have place P1, transition P1, and that's an arc. Okay? I can have something like this. P2, P3, okay, that's a legal example because I'm not connecting a place directly with another place or a transition directly with another transition. In this case, I write it once and I will write never again because it's useless, it's easier to understand graphically. But in this case, the flow relation is made of P1, P1, first arc, second arc, for example, P1, P2, third arc, P1, P3. Okay? So it's one of the many ways to describe who is connected with who. Okay? Just three arcs, 1, 2, 3, and so 1, 2, 3. Okay? This is a So the first thing that we immediately understand that the graph is a bit more complex, slightly more complex. So basically I can do more things because it's more complex. Okay? And that's the first part of the basic definition of Petri nets. Petri nets are then endowed with more quantities, typically. So this is called graph of the Petri net. And the Petri net is made by a graph of Petri net plus something. And this is called marking and weight functions. The P is a set of places, the P is a set of transitions, as usual. So the marking is a function between a set of places and a set of natural numbers. And the weight is a function between with the codomain equals to f and domain equals to n minus the number 0. It's just a notation. Okay, so what's the meaning of these two functions? These functions means basically that you associate an integer number to any place. Okay, and this is called marking because I usually graphically represent the marking, so this number associated to a place, as marks or tokens. Okay, so for example, I may draw like this is a typical graphical notation, to say that the marking of P1 is equal to 2. Okay, I alternatively say that I have 2 tokens or 2 marks in the place P1. That's an alternative way to say the same thing. Okay. Why this one is not more complicated? Simply, it says that I start from the elements of F, which I understand are the arcs. Okay, I have 3 arcs there, and I have 3 elements here, right? So it means that every arc is associated to a positive, strictly positive, non-null integer number. That's the meaning of this function. Okay, so I attach a number to these arcs. So, for example, I can attach this 3, 2, 1. I attach a weight to an arc. That's it. Okay, that's the form. So the definition is becoming even more, so even richer with respect to automata because I'm adding a few more information. Okay. On top of that, actually, I've not finished, because with automata, I would have finished a few words. Because when you define a transition function, you are done. Okay, you say that there is just one current state, and then you change state to the transition function, that's it. Now I have to explain or invent how to play with these quantities to make to build an evolution of the model, to build a behavior of this Petri net. So the behavior of an automaton is the set of arcs that you travel on. Okay? Now I have to define these rules. These rules are called execution rules or interpretation rules for the Petri net. Okay? Interpretation rules because in the past, somebody gave a slightly different interpretation of these quantities, but we, for sure, apply the standard definitions, so we can call them execution rules. The rules for which we can make a Petri net evolve. Okay? I think more or less it's clear so far. Okay?
Professor, I think I missed this because I was writing down. I understood that the arcs have numbers associated to them. What are the 2 dots in P1?
They are called marks. So this is mark or token. And this is the weight. and this is an arc.
Thank you.
So the execution rules, which define the real interpretation of the graphical symbols, are actually the heart of the Petri net. Okay, the clue is here, it's not in the structural definition. So this is based on two main concepts related to transitions. So transitions can be enabled and can fire. Okay, so we're talking about transitions, which can be enabled and can fire. Firing. In Italian language, this is called scatto, as you remember, scatto, scattare. I don't know in English, it's called fire, something like burn, but there's nothing burning here. Anyway, not yet, unless you really want. So the enable transition, so the enabling condition of a transition is not so complicated, but I try to formulate in words, and then I will show you the notation. Notation is more complicated, but the meaning is very simple. So transition is said to be enabled if the places that are in input are all marked with a sufficiently high number of marks, where sufficiently high means at least the same amount of the weight connecting that place to the transition. Okay? So I say it once more. So a transition is said to be enabled if a transition T, small t, is said to be enabled if for all the places in input, okay, just following the arrows, okay, it happens that all these places P has at least as many tokens, maps, as the weight connecting that place P with the transition P. So all these input places should be sufficiently marked, okay? And you understand this sufficiently marked just looking at the arc, okay? So in formula, this becomes a little bit long, but so T is said to be enabled, this transition T is said to be enabled, if and only if it happens that for every place belonging to the preset of T, which is represented by this symbol, so this means for any place belonging to the input places of T, it happens that the marking of the place P, which P? This one, which is for everything, okay, is at least equal to the weight that connects this place P with the transition T. Okay? So we say for the third time the definition of enabling. So it happens that the transition is enabled if all its input places have enough tokens, so have at least a number of tokens greater or equal to the weight of the arc connecting that place to the transition. Okay? And the firing of a transition only if enabled. Is associated to a change of marking. So filing the transitions amounts to change the tokens around the Petri net. Okay, the filing of a transition distributes the token in another way. Okay, and now I write like this: change of tokens. Okay, and this change is, to say, is very simple, because basically I have to remove tokens from the input places and add tokens to the output places. Okay, input and output just following the arrows. Okay, I have to remove some tokens from the input places and add some tokens in the output places, so those connected in output. Okay. How many tokens should I remove from input and put in output? As many as the weight. So it's very easy to understand. I should remove from input places as many tokens as the weight. And as well, I should add to output places a number of tokens equal to the weight of the arc connecting the transition of the places. Okay? So, I cannot fire this transition, right? Can I fire this transition? No, because it's not enabled. Okay, so I cannot fire it. So, firing is allowed only if the transition is enabled. Okay? And the rule is simple to understand, because if I would fire a transition which is not enabled, I simply don't have enough tokens to perform the operation. So I should remove 3 tokens when I have 2 here, so I cannot remove 3. I should go to -1, but tokens are like coins, coins in a box. Okay, if I have 2 coins, I cannot remove 3 coins. Okay. So it's easy to understand it. So this is not enabled. What can I do to transform, in my example, this transition into an enabled transition?
Okay.
I should add more tokens, for example. Or if this is just an example, I should reduce the weight. Okay? So let's draw everything clearly. Before firing, after firing. Let's do this example, make it easier. If you have colors, you can play with colors. I don't have colors, so I copy the picture twice. Okay. So now let's play with the tokens. Okay. So suppose that I'm having this amount of tokens. Okay. Let's play a little bit. I think you already have drawn the picture, so try to compute the situation, so the distribution of tokens after the firing, before the firing is already done, after the firing. possible. Okay. You should again realize that this transition is not enabled due to this arc, because the definition was for every place in input, it must happen that the input, the number of tokens should be at least equal to the weight. So for this arc, the transition would be enabled, but for this one, it's not enabled. So I cannot go on. So in order to go on, for example, I should do something like this. Now the transition is enabled. Now I can fire. So take a few seconds to compute the new mounting, and then we will together. So basically I apply the rule that I have not written because of simplicity. I know that I should remove tokens from input places and add the tokens to the output places for every single place. So here I have 2 tokens and I have to remove 1. So in the end I remain with 1. For this place, it's an input, so I should remove 2 tokens. I have 2 tokens, I should remove 2 tokens, in the end it's 0, so I'm done here. And finally, I should add tokens instead. So I have 1 token, I should add 5, in the end I have 6. 1, 2, 3, 4, 5, 6. Okay, so that's the situation before and after the firing. Okay, what do I understand immediately? What comes to my mind immediately? Immediately it comes out that the number of tokens is not constant at all. Okay, I started with 4, 5 tokens, and now I have 7 tokens. So the tokens are not constant in a Petri net. Okay, arrows are not pipelines through which the token passes. This is not like this. This is not a flipper. Okay, where tokens are balls, but the tokens may vary. Okay. This change, the motivation behind is that basically I use the tokens as identification of some states. Okay, they do not necessarily represent physical objects. It may be a possibility to use a token to represent a physical component. Okay, but I may use it to represent an abstract concept, like this robot is 3. What's the meaning of this robot is 3? Is there a sensor telling me that the robot is 3? Usually no, because maybe the robot is in the other room, okay, in the next classroom, okay, but maybe now is available to perform some work, and I need to use it to load the machine. I book it now, okay, and I use it in 2 minutes, the time that I need to go out of this room and enter the other room. So in these 2 minutes, the robot is doing nothing, but is booked for me. So it's not free for everybody if I reserve it, if I make a reservation for the robot, okay? So there is no sensor to say that the robot is reserved for me. So maybe you see the robot in the other room doing nothing, but this is why I'm taking some time to move myself and go there and play with the robot. Okay, so being free or being busy, it does not mean that the robot is moving continuously. Maybe it's busy because I reserved it. Okay, and I placed a reservation on it, and nobody else can use it except me. So it's not free. Okay, so this is an abstract concept. So I will use tokens to model, possibly, both abstract concepts like abstract states, as we usually do with automata, of course, as well as physical components. Okay, we will play with this next time. In English, the evolution of the Tetrinet is also called token play or token game, because it seems like a computer game. So some tokens disappear, some other appear. But what's important to say is that I have not finished with this, with the execution rules, because one basic rule is still missing. Okay, maybe some of you can guess what is the missing rule, what is the missing condition that I did not explain clearly so far. I didn't decide what to do if I have more than one enabled transition. Okay? So, I have another transition here, for example, two. And in this example, I have two enabled transitions. Okay? So, I have to decide what to do in this case. There are some formalisms that say that if you have more transitions enabled, you have to fire them all. And in other formalism, they say that you have to fire just one of them. But let's say just one of them. Okay? Others say you have to fire them all, like a sequential function of charge, subset. They are called synchronous languages because basically you move synchronously, firing all possible transitions. But this is impossible for us. Okay? With our notation, this is impossible. So in this case, I have to choose arbitrarily one transition to fire. Okay, T1 and T2 both are enabled. I have to choose one and then fire it. Okay, why arbitrarily? Because originally the Petrinets were used by Carl Adam Petri, which was a PhD at the time, a German guy, German student, PhD, modeling the flow of packets in a telecommunication network. So tokens were used to represent packets in a message, and transitions were used to represent a route, okay, a path from followed by a packet. And his goal was to understand what happens if a long message is broken into a number of packets, and then every packet follows a different route, but in the end, in order to rebuild the original message, you have to put all the packets in the correct order. So he invented this formalism. And the arbitrary behavior of Petrinets represent the fact that the packet may follow a route or another route, depending on the fact that one computer, one server is available or not. Okay, that's the original motivation. And then I said that with the notation that we have, we may have problems if we fire all the transitions, because in this case, these two are enabled. Okay, this is enabled, this is also enabled. But I cannot, I could not fire both of them, because I should remove one token due to this firing and another one token due to this firing, but I have just one. So I really cannot. Okay, so with our definitions of Petrinet, we cannot fire more than one transition. Okay, so that's totally coherent. So in our rule, there's only one transition can fire at a time. Okay, at a given time, only one transition can fire. This basically amounts to say that all events are asynchronous, okay, and they cannot overlap in time. So they are so fast that they cannot overlap. So either one event becomes before another one, or vice versa. And one event occurs, it changes the state of the net, changing the token. Okay? So in this example, if you choose T2, you remove this token here, and this transition that was enabled does not is no more enabled after the firing of T2. So it follows this rule. Okay? You have a marking, you compute the set of enabled transition, you pick one, you fire it, you change the marking of the net, and then you start again. Compute the set of enabled transition, you pick one, you fire it, you change the marking, and you go on. The marking is basically the state of our system. The transition is basically the transition between states. The transition of the Petrinet represents the transition between two different states, two different markings. Okay, you are in a state, you choose which transition to fire, you change state, you change marking, and then what was enabled before maybe is no more enabled. If we both are two robots and we have just one product to pick, he's free, I'm free, we are both free. But if I am faster than him, what happens? That I can work and he cannot work anymore. Okay, so in this situation, we both can work. In this situation, I only can work. So the event peak of the product has become first. So I'm changing the state of the system. He was first in a condition to perform something. Now he's in the condition that he cannot perform anything. Okay? So this is very good to model what? To model shared resources. Okay? This is a possible shared resource between me and him. And the first who pick it is the first who can enjoy the resource. That's it. Okay? So that's it for today. We go on next time.